Hello students, today we will see exercise 1.2 of first topic mathematical logic. There are three types of examples in this exercise. One, that is the construction of truth table of the given statement pattern. Second type, prove the logical equivalence of given two statement patterns. And third one, that is to examine whether the statement pattern is tautology, contradiction or contingency. For this, first type of example, let us take this statement pattern. P or negation Q implies R and P. Let us call this is equal to A. Let us call this statement pattern by A. To prepare the truth table, we have to determine the number of rows and number of columns. We can determine the number of rows for the preparation of this truth table. It is equal to 2 raised to n plus 1, where n is nothing but the number of simple statements in this statement pattern. Here P, Q and R, these three simple statements are there, number of simple statements. So the number of rows becomes 2 raised to 3 plus 1, that is equal to 9. 2 raised to 3 is 8 plus 1, that is 9. And the number of columns is equal to the number of simple statements plus number of logical connectives. This number of simple statements, obviously 3 here, and number of logical connectives 1, 2, 3 and 4. So we have 7 columns for this truth table. So we need 9 rows and 7 columns. Let us try to prepare the truth table for this. The first simple statements are 2, P, Q and R. So it is P, Q, R. You know the possible combinations of truth values of P, Q and R are P, T, T. First we are taking all T's. After that T, T, F. Third one is T, F, T. Fourth one T, F, F. Next F, T, T. After that F, T, F. Next one is F, F, T. And last one contains F, F and F. So total 8 combinations are there. In these 4 T's and 4 F are there in first statement pattern or column. For second statement, 2 T's, 2 F, 2 T's, 2 F. Here 1 T, 1 F, 1 T, 1 F, 1 T, 1 F, 1 T, 1 F. So we get all these possible combinations. Now to prepare this table, we need negation of Q. So we will write third row as negation of Q. Fourth one of this bracket, that is P or negation Q. Then R and P. Next one, the implication of these two, that is P or negation Q implies R and P. Let us vector the column of negation of q. Negation of this is f, f, t, t, f, f, t, and last one is again t. Next, p or negation q. P is here, negation q is here. There, disjunction means we will find whether t is there. If t is there, then the conclusion will be t. So this is t, true. This is also true. This is true. This is also true. Here false and false. Here true and true. Now next column is of R conjunction P. R is here, P is here. So take the conjunction of these two. In conjunction, we will find whether F is there, false statement is there. If someone is false, the total conjunction is false. This is true because both are true. Here is false because one is false. This is again true. This is true. This row is also true. Both are false. Sorry. In this column, one is false. Both are true, therefore true. Here is one false, so false. False, 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 false. Remaining all are F. So this is the conjunction of R and P. Next, P or negation Q and R conjunction P, their implication. So implication T is T. T implies F is F. T implies T is T. T implies F is F. F implies F is T. Only when T implies F, we get F. Here F implies F is again T. T implies F is F. And T implies F is also F. So we get TF, TF, TT, FF. These are the entries in the truth table of this statement pattern. So this is the preparation of truth table of the given statement pattern. Let us see one more example. Simple example. P implies Q implies P. Here we have only two statements. So we need P, Q, and logical connectives are only two. So in all two statements and two connectives, so we need only four columns. Next one is Q implies P, and after that P implies Q implies P. As there are two statements, so combinations are like this. TT, TF, FT, FF, or remember as TT, FF, TF, TF. Then Q implies P. P implies T is P. F implies T is P. T implies F is F. And F implies F is T. Now P implies this. So T implies T is T. T implies T is T. F implies F is T. And F implies T is again T. So this is the preparation of this small statement pattern. But sometimes, if you observe here, third type, then examine whether the statement pattern is tautology, contradiction, or contingency. Let us check this third type in this first type of examples. After preparation of truth table, what we can conclude from this fourth column, that in the column of this statement pattern, all entries are T. So obviously this statement pattern is a tautology. But if you observe this statement pattern, then the entries in the column of this statement pattern, some are T's and some are F. So this statement pattern is contingency. Let us see second type of example, that is to prove the logical equivalence. First example, P and Q implies Q or P. We have to check whether this statement pattern is tautology, contradiction, or contingency. For this, let us prepare the truth table again. P, Q, P and Q. Third one is Q or P. And last one is P and Q implies Q or P. As we know, these entries are PTFF, these are PF, TF. Then P and Q, it is P, F, F, T. Q or P, it is T, P, T and F. Now let us take the implication. This implies this, that is P, F implies T is T, F implies T is also T, and F implies F is also T. So this statement pattern is tautology. So how to write the conclusion? Here in the column of statement pattern, P and Q implies Q or P, all the entries are truth values, are T, therefore P and Q implies Q or P is tautology. This is the way to determine whether this given statement pattern is tautology, contradiction, or contingency. Let us take another example which contains three statement patterns. Simple statements. Negation P implies Q. And P and R. So basically, we have taken these three columns. After that, negation P, then negation P implies Q. Next one is P and R, and last one is this. That is negation P implies Q and P and R. Let us prepare the table for this. Negation of P. Negation of P is F, 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 T, T, T and T. So negation of P implies Q. F implies T is T. F implies T is T. F implies F is T. F implies F is T. T implies T is again T. T implies T is T. T implies F is F. And T implies F is F. Let us see P and R. P and R. Conjunction of these two is T. Conjunction of these two is F. T, F, here F, here both are F, so again F, one is F, so as both are F, so F. Because in conjunction you will observe whether the statement, one of the statement is false or not. Now last column, which is of the conjunction of these two, conjunction of this and this. So conjunction of these two is T, conjunction of these two is false because one is false, both are T, so T, one is false, so false, one is false, here is one false, at least one false, so remaining are F, 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 F. So in last column we get T, F, T, F, 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 F. So below this table we will write conclusion as in the column of statement pattern, negation of P implies Q and P and R. Entries means truth values are some P and some are F. So therefore the given statement pattern is contingency. The given statement pattern is contingency. So this statement pattern is contingency because we have some P's and some F. This is the second type of example. Let us see third example. Negation P and negation P and P or negation Q and Q. This contains only two statements, simple statements. So it has truth values TTFF and TFTF. Second, negation P and is there. Negation P, after that negation Q, after that P or negation Q, then P or negation Q and Q. In last column, we will call this statement pattern as A, so it is of A. Let us see, negation of P is F, F, T, T. Negation of Q is F, T, F and T. Next, P or negation Q. P is here, negation Q is here. We have to take conjunction of these two. In disjunction detail, we will find whether some T is there or not. Here is one T, so T. Here is both T, no T, so it's F. 1t, so it's a t. Now we have to take the disjunction of this statement with q. So disjunction of these two, we will find whether f is there. No f, so t. Here is one f, so f. Here is one f, so f. Here is one f, so f. Now last column, which is of the conjunction of negation p and this column. Negation p is here, and we have to take the conjunction of these two. Here is one f, so f. Both f, so f. One f, so f, and last one is one f. That's one. So in the truth table of this statement pattern, if you observe, the last column contains all f. So what to write here? Since the column of the last column of given statement pattern contains only f, therefore the statement pattern, this E, is contradiction. So we have taken three examples of determination of tautology, contradiction, or contingency. In first example, we have taken example of tautology. In second part, we have taken example of contingency, and in this third example, we have taken example of contradiction. Now let us see the second type of example, that is the proof of logical equivalence. Negation of P or Q or negation of P and Q. We have to prove using truth table. We can prove this also without using truth table. Using properties also we can prove this, but now we will prove this by using truth table. So these two statement patterns contains only two statements, P and Q. So we need this type of table containing 5 rows. Now let us form the columns. We need negation of P here, then negation of P or Q, negation of P and Q, and conjunction of these two, that is negation of P or Q and negation of P and Q. And last column, that negation P is already there. So we need these 1, 2, 3, 4, 5 and 6 columns only. Let us complete this truth table. Here negation P means obviously you get F, F, P and T. Then negation P or Q. Negation P or Q. Disjunction of these two. P, F, P, T. Negation of P and Q means conjunction of these two. That is F, F, T and T. Last one, the conjunction of these two. That is F, F, P and T. So if you observe these two columns, column number 3 and 6, 3 and 6. If the entries are F, F, T, T, here are also entries F, F, T, T. So the entries in these two columns, corresponding entries are identical. So these two statement patterns are equivalent. So how to write here? Conclusion: as the corresponding entries means truth values, in the columns of given two statement patterns are identical. Therefore, negation P or Q and negation P and Q is equivalent to negation of P. That is the way to write the proof of this question, that to prove this statement pattern is equivalent to this one. Let us see one more example of this. Negation of P by conditional Q, which is equivalent to P and negation Q, or Q and negation P. Again, these two statement patterns contains P and Q, only two statements. So we need this 5 rows table. Let us see the requirement here. Once again, we will prepare the columns required for this equivalence. First one is P by conditional Q, its negation, that is negation of P by conditional Q. Next we need negation Q. After that, P and negation Q, P and negation Q, then negation P, and after that Q and negation P, and in last column we need P and negation Q, or Q and negation P. Okay, let's complete this. By condition, both are same, so T. Here both are same, so T. Negation of this is F, P, T, F. Okay. Then next, negation of Q, that is F, P, F, T. Next, P and negation Q, P and negation, conjunction of these two. Conjunction means I have to find F. Both are T, so T. Both are F, so F. One is F, that's why F. Negation of P, it's F, F, T, T. Then Q and negation of P, conjunction of these two. Conjunction means we will check whether F is there or not. If F is there, the conclusion will be F. No F, so T. One F, so F. Now last contains the conjunction disjunction of this column number 5, 6, 7, 8, 9. This is the conjunction of column number 6th and 8th. So F or F, no chance, obviously F. Here T, here is T, and here is F. So if you observe column number 4 and 9, 4 is of this left hand side of equivalence and 9 column contains the right hand side of given equivalence. So we have to prove this. So to prove this, we have prepared this table, and from in this table the column number 4 contains entries F, T, T, F, column number 9 contains entries F, T, T, F. Means corresponding entries F, F, T, 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 T and F, F. All these corresponding entries are identical. So we will write conclusion here. The corresponding entries means truth tables, truth values in the columns of given two statement patterns. Which are those columns? In the column 4 and 9 of given two statement patterns are identical. So these two statement patterns are equivalent. Therefore, the given two statement patterns are identical, sorry, equivalent. That is negation of P by conditional Q. It is equivalent to P and negation Q or Q and negation P. This is the proof of logical equivalence. So to remember, if logical equivalence is asked, first find the number of simple statements from that number of required rows. Then logical connectives, as there are 1, 2, 3, 4, 5, 6 and 7 logical connectives. So we need 7 columns plus 2 simple statements. So total 9 columns are there. Prepare the columns of parts of that statement patterns, and this is 4 column contains left hand side and 9 column is of right hand side of this equivalence. So check whether the corresponding entries are identical or not. If they are identical, they are equivalent. If these corresponding entries are not identical, then you can write the given statement patterns are not logically equivalent. So sometimes proof is asked for logical equivalence. Sometimes check whether these two statement patterns are logical equivalent or not. So if such type of question is asked to determine the equivalence of these two statement patterns, you have to prepare the same type of table, and from columns of these two statement patterns you can determine whether they are true, they are